Hello everyone, welcome to the another session of digital signal processing. In the last session, we had started discussion of fast Fourier transform, and we had discussed that fast Fourier transform can be calculated in two different ways. One way is called as decimation in time, another algorithm is called as decimation in frequency. So in the last session, we had covered decimation in time, and today we'll be discussing what is decimation in frequency FFT algorithm. So in this decimation in time FFT algorithm, what we had done, we had decomposed the given sample to calculate the DFT. We dividing that sequence sequentially, split that input sample xn in time domain into set of the smaller and smaller subsequences, and then we were trying to form the weighted combination of DFTs to calculate the overall DFT. So overall we were using divide and conquer approach. So decimation in frequency is no different than decimation in time. As the name says, the decimation is carried out in time when I talk about decimation in time algorithm, and when we'll be discussing decimation in frequency, that same decimation would be performed in the frequency domain. That means if I talk about this DIT, I'm decimating the samples xn, and when I'm talking about this DIF, I'm decimating the samples xk. So everything that we had discussed in the last session about decimation in time, that would be completely same process but in the reverse direction. We'll be starting with xk samples and start subdividing the sequence. So the second algorithm that we are going to discuss is decimation in frequency. It also decomposes the DFT by recursively splitting the sequence of the element, that is xk, in the frequency domain into set of the smaller and smaller subsequences. So to derive the decimation in frequency FFT algorithm, if I have total number of the samples as n and I am taking the power of 2, that means again I am talking about another algorithm in radix 2. So the input sequence xn is divided into first half and last half of the point. So this comes here, the second difference between DIT and DIF. The first was I was splitting xn, here I am splitting xk, and second thing is, as we started decimation in time domain, I divided the sequence into even and odd samples. But when I start dividing the sequence in frequency domain, I do not consider these points of even and odd. I first divide my sequence into half and half. So if n is equal to 8, I have to divide into 4 and 4. But these 4 would be first 4 samples and these 4 would be the last 4 samples of the given sequence. So how to proceed for this decimation in frequency? If we talk about, say, n is equal to 8, then in the same way I'll be proceeding out. I'll be creating parallel lines equal to number of samples to which I need to calculate the DFT. So as such, I should start from xk domain, that is from the right hand side of the graph, and here I must give my input samples xk, and here my samples xn would be here. So later on we'll see that the same algorithm would also be used for calculating the inverse DFT as well. So this is the right hand section where I need to start from. So in the case of DIT, how the samples were taken up, whatever samples were there in this particular domain, I was dividing those samples into subsamples and perform that particular calculation. So the first stage in the reverse direction would be, I would cross these sets of samples. That means I'll be considering n by 4 samples. If it is 8, then 4 and 4, and then 2 and 2 samples. So I'll start plotting the graph from the lowermost stage and would cross up these 2 sets of input samples. That is my first stage in the case of DIF algorithm. Similarly, in the second stage also, I would consider a set of these 4 elements and a set of these 4 elements, upper 4 and lower 4, and would start making the graph connecting alternate line, 1 with 3, 2 with 4, 3 in the reverse direction with 1 and 4 with 2. The same pattern would be repeated for the lower samples as well. So that corresponds to my second stage of decimation. And in the last stage, I'll consider all the 8 samples here and would start connecting first and fourth, second and next, second, third and third of next element, and in this way I would start crossing the element in the reverse direction as well. So that comes out to my third stage of connecting the samples, first half and the second half samples. So if we can map the two algorithm DIT and DIF, if I look at the graph from the right hand side and move toward the left hand side, this looks like the DIT graph itself. So that is, we say we can start from the XK and start repeating drawing the graph in the same way. Or if we feel comfortable from left hand side, then we say we start third stage first, following the second stage and the first stage. So I may first connect 8 points, then 4 points and 2 points. This is completely my wish, how I feel comfortable in drawing this particular graph. So how this algorithm works, I have taken up this XK into 2 subparts. So if I have n number of samples, algorithmically I would divide them into n by 2 and n by 2, first half and last half, and this would range from 0 to n by 2 minus 1, showing the first half, and n by 2 to n in the second half. So this is here, this XK has been divided into these 2 subsequences, one ranging from 0 to n by 2 minus 1 and second ranging from n by 2 to n minus 1. So if this xn is my first half sequence having n by 2 number of samples, so this n samples can be represented by variable n, and all the samples in the second sequence can be represented as n plus n by 2. That means if I take the first sample, n is equal to 0, the first sample in the second sequence would be n by 2. So if I talk about 4, that is first and fourth sample. So this is what we are showing over here. The first sequence is represented by n and second sequence samples are represented by n plus n by 2, the way we have shown over here. Now what has to be done? The power of this w would also get changed, n and n. This would remain n, but power of n now here would be n plus n by 2. Same has been shown over here. So I would simply open up this bracket and try to create 2 w's, that is wn raised to the power n dot wn raised to the power n by 2, and k being common to both the samples. So simply I am rearranging. This is my first summation and this is my second summation. One is wnk showing this part and another is wn by 2k showing up this part. So now if I have to solve this twiddle factor value, that is wn n by 2, let me open up in the form of the exponential. So that is e raised to the power minus j 2 pi by n by 2. So this n cancel out this n, 2 cancels out this 2. So I am left with e raised to the power minus j pi k. So if I have to solve for this in the form of trigonometrical expression to get a value, cos of pi k minus j sine of pi k, that is minus 1k. So this factor can be replaced here and written as minus 1k. Now these two samples, that is the first half sample and last half sample, either they would be added or they would be subtracted depending upon the value of k, if k is even or if k is odd. So let me take these case of k even and odd. If k is even, xk is shown as x and k is 2r. And for odd part, this is 2r plus 1. So putting up these value here in the previous equation, if I solve for k is equal to 2r, that is even value of k, the summation would open up like this, 2r, this minus 1 would become positive. So all the samples of the sequence would get added, weighted by wn by 2 raised to the power n. But if I solve for k is equal to odd, replacing k with 2r plus 1, I see minus 1 raised to the power 2r would be even positive value, but there is another factor, that is minus 1 raised to the power 1. So ultimately this summation is going to come as minus 1. So if this k is odd, I see that these samples of first part and second part sequence, they get subtracted. So if we see this algorithm in the form of the graphs, I see in the first stage of decimation, when I am dividing it as n by 2 sequences, this g0 value, it is x0 and x4 added together, x0 plus x4. But for another part of the sequence, if I talk about this particular case and this sample, so this is x0, x4 multiplied by minus 1. So this h0 comes out to be x0 minus x of 4. So if first part of the sequence is an even part and say this is the odd part, I see in the first section all the samples which I get, G0, G1, G2 and G3, they would be additions of all the samples. And all the samples in the lower part would be subtraction of these samples. So this algorithm says that upper part, that is G0, 1, 2 and 3, that is addition of samples. 0, 1, 2, 3 are first half samples, 4, 5, 6, 7 are last half of the samples. But when I calculate H0, 1, 2 and 3, which is the lower part value, they are the difference of these two values. So this is how the first stage graph comes out with the algorithm. Similarly, we can solve for the second stage of the graph, and similarly other points can be calculated. So this algorithm can be extended up to any stage depending upon the value of n. So this is a example numerical in which my xn, here n is equal to 8, getting the sample 1, 2, 3, 4 in the first half and 4, 3, 2, 1. Talking about the weights, how to weigh up these samples, like if we are talking that G0 is the sum of these two values and these two values should have certain weight. That weight here being represented as Wn by 2 raised to the power n. So these are nothing but simple weights W1, W2, W3 and W0. So I would add up these samples first and then I would multiply it with a certain weight, whatever is the weight, W0, 1, 2 and 3. So this is another difference between two algorithms. In DIT, we were first multiplying the signal, like x4 was weighted here and then added to the first sample. But in the case of DIF algorithm, I would add up or subtract the samples first and then I would multiply it with the respective weight. So looking on to this example, I have to divide this particular sequence 1, 2, 3, 4 and 4, 3, 2, 1 as first half and second half. That is the first stage of decimation. Again, this can be divided as first half and second half. Similarly here, this is 4, 3 and this is 2 and 1. And finally, what I am getting first half and the second half? 1, 2, 3, 4 and 4, 3, 2, 1. So what do I see? if I keep on dividing the sequence as first half and second half, there is no difference in the input samples from the xn side. So in summary, what do I see when I am creating DIF graph? From the left hand side, the input sequence which I am giving to the graph, that would be ordered. It would be inputted to the graph in the same order which has been provided to us. So how this particular graph is being created here? I'm starting from the left hand side. I'm plotting the graph, 3-stage graph first, third stage of the graph, then I'm plotting the second stage of the graph, and then the first stage of the graph. So what do I see? I'm giving the input in sequence. Weights are W0, W1, W2 and W3. Whatever samples I'm calculating here, I'm giving to the second stage, and my weights are same, 0, 2, 0 and 2, with -1 being alternatively provided. And in the third stage, my weights are 0, 0, 0 and 0 alternatively. So how this graph is working? In the first stage, this sample is being multiplied by this sample. So here it is 1, here it is 4, 1 plus 4 comes out to be 5. Here I do not have any weight, that means I am multiplying it with 1. Looking at this lower sample, this is being multiplied with the weight -1, 4 is multiplied with -1, that means I am getting -4, and here I am getting 1. So -4 plus 1 is -3, and corresponding weight which is being assigned here is W08. That means I simply multiplied -3 and W08 is 1. So I am multiplying this one, I am getting -3. Looking at the another sample, that is this, and a sample coming out from the upper half. So here I am getting 2, 3 into -1 -3. Now weight is W18, which is 0.707 plus J 0.707. So these samples are multiplied by this particular weight and inputted to the second stage. So this pattern would be repeated, and at output what do I see? X0, X4, X2, X6, 153537 means input was ordered in a sequence which I had provided, but output is unordered. And the pattern of this unordering is even and odd. These all the samples are even, these all the samples are odd. So this is another point of difference between DIT and DIF algorithm, that input is given in the ordered way and output is received in the unordered way, which is completely reverse of what we have done in the DIT. So this is even part and this is odd part, decimated twice in stage of n/2 and n/4. So this was all about this particular algorithm. I was telling you that this algorithm is being used for calculating the inverse as well. So the next topic of discussion would be inverse fast Fourier transform. So this is all for this session. Thank you.